Hello everyone, I'm here to share our work on improving imbalanced regression through geometric constraints. My name is Ilay, a fourth-year PhD student. This is a collaborative work between National University of Singapore and Duke University. In this work, we introduce surrogate-driven representation learning, or SRL, which improves imbalanced regression by enforcing feature uniformity. Through the statistical visualization, we examine the feature distribution under two imbalance scenarios, where the uniformity regions are pointed by the arrows. The baseline methods tend to create clustered, uneven representations. Conversely, through proposed geometric constraints, we achieve uniform coverage across the entire feature space. The colors represent different label values, and you can see how our method spread the entire range uniformly across the sphere, which benefits the minority samples. Imbalanced regression is everywhere in real-world applications. For example, for age estimation, we may have a lot of data from middle ages, but very few samples from young children and elder people. This creates major problems, including performance degradation toward minority groups or representation collapse. Previous method focusing on problem through the reweighting or resampling. In this work, we approach this challenge from the representation learning perspective. This brings us to the feature uniformity, a powerful representation learning concept. The idea is simple: preserve maximum information by spreading feature uniformly across available feature space. This idea has been applied to solving the long tail classification, where its aim is to maximize the distance among distinct clusters for each classes. However, in the case of regression, we need smooth, continuous transition between different values. This is where our geometric approach comes in. Classification creates distinct clusters, like separate balls of yarn, but regression needs one continuous thread that smoothly transitions from one value to another. Therefore, our key insight to this problem is this analogy. Imagine winding a yarn around a ball. We can imagine the yarn represents the continuous trace of representations, and the value change. The ball is our feature space, a hypersphere. And our goal is to wind the yarn to cover the entire ball surface uniformly without gaps or overlaps. We introduce two complementary geometric constraints, enveloping loss and homogeneity loss. The enveloping loss is to maximize the volume of the tube occupies on the sphere. This encourages the trace to spread out and explore the entire surface. And the homogeneity loss encourages even spacing along the trace. We minimize the variance in arc length between the consecutive points. Together, these losses create representations that are both space-filling and smoothly distributed. Now, let's take a look at how the process during training. One challenge for this method is that each batch might not contain all the label values, especially for minority samples. Therefore, we build and maintain a surrogate representation. So first, we will get the embedding from the current batch. And for the missing label ranges, we will refill them from the saved centroid from the last mini batch. Then we average the representation within each bin to get the centroid. And after that, we calculate and optimize based on our geometric loss on our representation surrogate. Finally, we update the momentum for smooth transition across different epochs. Now, let's take a look at the result. Here is the result for the age estimation task. We visualize the performance gain across the whole age range. The gray areas represent the original label distribution. We can see that there are a lot of middle-aged samples and very few at extremes. And the solid blue bar represents the performance gain. We can observe that the biggest improvement coming from the extreme, the minority cases, the elder and the youngers, which indicates that enforcing the uniform representation will prevent the model from ignoring the minority cases. We also did experiments on other data sets, including tax similarity score and the real estate price. You can refer to our paper for more details. Besides, we conduct extensive ablation study to understand our method better. The heat map on the left shows the different weight combination for our losses affect performance, which also indicates the significance of balancing the geometric properties. On the right-hand side, we calculate the percentage of different label range with respect to the whole feature space. We can see that by using our method, the few short regions increased its proportion from 4.5 to 22, which also explains why the performance gain on the minority regions. So put it together, to summarize our contribution, we introduced a new paradigm, thinking about regression through the geometric uniformity. And on top of that, we propose two loss functions, the enveloping loss and the homogeneity loss. One limitation of our method is currently the SRL only handles single-dimensional regression targets. Therefore, we call attention on the future work will extend to the multi-dimensional output and more complex label structures. Thank you for your time.